Hello, my name's Thomas Gary, and I've been working with Zonta Nguyen to work on the ultrasonic inspection with Kelvin Voigt wave equation. In this problem, we're using an actuator to send a vibration down a long semi-infinite steel cylinder rod. In this problem, we're trying to find the amplitude attenuation and the phase shift. Basically, we want to locate any failures in industry. Any engineers that are creating a long cylinder steel rod want to be able to detect any stress points or crack areas where crack propagation is happening. And this is used in the field to create safety and a better material for any
We assume
project.
that the cylindrical rod is long enough in the axial direction, x, such that the diameter is negligibly small, and because of that, we can model our problem using a one-dimensional model. From here, we prescribe the initial conditions that the bar is at rest, and we prescribe a boundary condition such that the transducer at the very beginning of the rod is applying a prescribed harmonic function that eventually decays to a steady state as we approach the other end of the bar. Because of our model, we can model our problem using the partial differential equation for a one-dimensional wave that is damped using the Kelvin-Voigt model. Using the harmonic ensemble approach, where if a prescribed frequency is applied at one part of the system or at the beginning of the system, that frequency remains the same throughout the system with an amplitude decay or attenuation and a phase shift. Because of that, we set we set our u of xt equal to the real portion of the following term. We substitute this term into the PDE, yielding a second order ordinary differential equation where the rest of our coefficients can be simplified to a term k squared, which is a complex number. We get the solution for our ordinary differential equation, and rather than trying to find the square root of a complex number, we instead set that complex number equal to a term kr, where kr is equal to the real term and alpha is equal to the imaginary term. We find the square of that, and by doing this, we can instead use substitution, the quadratic formula, and various other algebraic methods to gain our terms. After this, we find that when putting it back into the u of xt term, the real portion of the k constant is equal to the function delta for phase shift, and alpha is equal to our amplitude attenuation. Because of that, we redefine our parameters such that attenuation is equal to alpha, and delta is equal to the product of x and our previous k of r term. We substitute these back into the PDE, apply Euler's formula so that we can get periodic functions, and because the harmonic ensemble approach only takes the real portion of the solution, we end up removing the imaginary term from Euler's formula, which gives us the final solution. U of xt is equal to c e to the power of negative ax cosine omega t minus our phase shift delta, where a delta are given with the following parameters set.
Now looking at our actual problem or PDE in motion, we can actually see the graphs. If I go to run the program, we get not only our amplitude, attenuation, and phase shift, but we also get a nice clean graph with it. We set the value to whatever L we want and use the values we found online for steel to actually get a graph which shows how the wave propagates through the system. It also shows an animation, as you can see here, very slowly moving when we go over the course of 5 seconds.